Hello. In this video, I will be explaining about binary search tree implementation in C# language. And first, I will be writing the structure of the binary search tree. Most of the time, binary search tree is used for implementing a search across a sorted array, and we will be using a tree structure so that we can search to different parts of the tree. And also, I will be explaining line by line implementation of binary search tree through my code, and I will explain the different traversals, how they will be used and and operated through C# language in this case. So let's start with the coding. Yeah. Okay, so we have opened our VS Code, and the first thing we need to write is the structure of our, our tree node. Our tree. And before writing the structure of our tree, we need to declare the structure of our node, which would be, first of all, it would have some value, and then it would have another tree node named left. Left. Similarly, it will have another tree node named right. Now that we have a basic structure of the node, we need to create a structure for our node, which would which would clear. So whenever we create a node, we can enter or give a default value to these attributes of the node. So int the value of val would have a default value of 0. Tree node left would also have its default value as null, and tree node right would have the value of null. So whatever, if these parameters are not declared or are not given any value while calling the constructor of the node, then they would have a default value. Hmm. Now we give them the value, and if there is a different value passed in these parameters, then that would be passed on to the actual value of these attributes. So now we have created the structure of a node in the binary search tree. And what is left now is the basic structure, or we can say the main structure of a binary tree, binary search tree. It would be better to call it binary search tree. And obviously, this would contain a node, and let's just say this node to be a root. What we would want to do is that in the binary search tree, we will assume that there is a single node, and that node is then further connected to different nodes. And or at a certain time, there would be a single root, and it would have two children. In a binary search tree, there can be a maximum of two children only, and this constraint is taken care of by introducing these two attributes in the tree-node class. So what we'll be creating now is a method which would operate all the operations like search, insertion, and traversals in the binary search tree. But before that, I need to pass a tree node, which is actually a root, and that root would have a value, because if I talk about a searching algorithm, then in that algorithm I would need I would need to search a value. Same in the case of insertion, I would need to insert a value to a root. The root can be can be any any uh, any tree, any subtree within a tree. For example, if there is a main root, it does not mean that I have to create different root for each layer. With this, I can use a single root again and again and find its left and right root. And this string operation parameter will be used to declare what operation we would be doing. The first case in this method is if the value of the root is null, which means the binary search tree has currently no element. Then we would add add a new node to this tree, and we will exit from the from the if loop, or we will exit from the method. And through this, if we have a root if we don't have a root, then it would automatically create a root with the value that is passed on in the parameter. Let's have Now let's come to the operation part of our code. If the operation is insert, if the operation is if the operation is insert, then we would first check that if the node node let's see the root. Wait a minute. I think what I mean right here is a node, because what I am sending here is different than this. It might be different than this, because at one point of time it is actually a root. But when I will do recursive calling to left and right nodes, then it would not be a good option to write this parameter as root, because actually when I will recursive call this method inside different operations, then I would not be passing a root into it. Instead, I would be passing the left node of the root or the right node of the root. So that is why it is better to name it node. Now, if node is equals to null, then node would be new tree node with this value. So let's just say that if we are at a position where we have to insert a value of node to any of the leaf node. Now leaf nodes do not have another node. So the child nodes of a leaf node would always be null. And if we want to insert a node to a leaf node, then we would have to use this line of code. When if value is less than the value that is present in the node 12. Now this is where the recursion part would come. We want we want our code to go to either left or right based on the value that we want to add our node. So if the value is less than the value of the node, then it would go to the left node. It would go to the left node. So it, it would look like this. And then we would exit from the loop, exit from the statement, and we would now use recursive call in which you would pass the left node of the present node with the value that we want to insert, and the operation is the same as which was given in this if statement. So insert. So what will happen is that if the if the value here is less than this, if it is just a minute. So, so this would happen. There is one step missing here. Is that I write? I need to check here that if actually the node left is equals to the value that has been passed here or not. Wait a second. Yes, it is 49. Okay, then now it is that I actually have to find a place where I have to insert the node. Now it is obvious that where I would be inserting something prior to that instance, there was nothing there before insertion. So this is what I'm checking here. And the earlier problem that I was having, I did not declare this event here, due to which it would it would create an error while running this code. That is why I had changed it. Now, after this, if this is found, until this would run only and only if the left node is null. And how would we go through each of the left node in every instance to find whether we come across this situation or not? It is through this method, which is a recursive call. Similarly, we will do the same for the for the right side of the value. If the value is greater than the value of the current node that you want to add, the value which you want to add is greater than the value of the current node, then we would write the same logic as was written before. If node dot write is equal to null, then node dot write is equal to new tree node with the value to be inserted, and then we would exit from the statements on in whichever loop or recursion we are having, we will exit from it. And this instead of left we will write here node dot write, and the same operation will be passed to this recursion. Now we have done the insertion part of binary search tree. So let's go to the other part, which is the search part of our binary search tree. Then we will check. First, we will see if the node is null, or if the node dot value is equals to null, is equal to the actual value that we are trying to find. If it is null, either in those of the cases, we would have a one-liner answer to it. And if the node is null, we would say not found. If the value of the node, the first node that on which it starts searching is the node where the same value is found, then we would say found the value. Now, as it is a simple if and else statement, then we will use a ternary operator to to display this if and else relation between them. Simple. No dot where. This would happen if node is not equal to null. This would happen if no node is null. One more thing is that we return here nothing else. If we are not returning anything, it means that we're exiting from this block of code. Right. Now we have to check if the value is less than the current node or not. Actually, the command that we have to write in this statement is only a one-liner command. So it will be okay if I just use a single, if I use this statement through one line only. If the value is less than node.val, we will apply the same logic. It would go across the left node because this is how the structure of binary search tree is formed. A main node, the in the left side of the node, there would be the node whose value is less than the root node, and on the right side, it would be that node whose value is greater than the value of the root node. Now, this is where an operation, and we would try and operate in other case where the value is greater than the node value, then we would recurse through the right part of the node, so right side of this. You can say right side. Now this was the search. As you can see, the search is quite simple, but now what we have to think about is the traversal across the tree. For that, first we will write for in order. For in order, what happens in order traversal is that we first check. Now, we would be using recursion as usual in this case because we need to recurse through a recursion. We have to recurse through a tree, and we have to recursively form a function until the value of node is null, which would only arise when we reach the leaf node of the tree. Now, what happens in order is that we first of all we first go through the left node, and then we go through the root node, and then we go to the right node. So console or write line can use node dot val is operate. Again we write operate and go to the right side operation. It would see and it would imagine that what would happen if this code is executed. It is at first, if we start from the root node, we know that root node is not null in a tree which actually exists. So the root node would not be null, then we would start to the left side. We go to the left node, and when we go to the left node, we again enter this method. And in this method, we are already passing the same operation that was here. So when we enter this method, we would eventually reach this code again. So in this code, when we are already in the left node, we would again go to the left node, and we will again go to this method and enter this block of code. After that, we would keep on traversing through the left node until we reach the leaf node, because at that time we would get our base case. And after that base case, we would go back to the second line of code of the last method that was called. So let's just imagine that this was we are currently on the last leaf node, and as this node is not null, and we start by going to this line of code, and when it is executed, we we increment, or we don't increment actually, we just go to the left node of a leaf node. Now, as I said earlier, that the left node of a leaf node or either the right node, they both are null. So once we again go to this method and reach this operation, then this if statement would not execute. So we would come back to the instance where we had our node as a leaf node, and would execute the root value of that leaf node. We would print this root value, and once it is printed, then we will go to the right node of that root node, and once that is done, then we go back to the previous previous root node of the left node. So this is how in order would execute. Similarly, we would write for pre-order. In this order, what would happen is that first we would go to the root value, then the left, and then the right. So same thing, if node is not equal to null, if node is not equal to null, then just can paste this. We will follow the same case in post order. In post order, everything is same except the root value is traversed at the end after we traverse the right node for looping. Now we have created the binary search tree structure, and now we have to create a main method, main function, where we would create a binary search, an instance of binary search tree, and in that instance, we would test if our code runs well or not. First of all, let's just create an instance of a binary search tree. Let's start with BST operation, BST operation in which we write the root. Now I know that we have not declared, or we have not given the value to the root of binary search tree, but as we discussed while writing the code, in this line of code, if the root is null and I have already called this method, we can see that in this method I am also passing a value. Then our code would be smart enough to pass that value to the root node. So let's do 15 and then insert. Similarly, I'll add Add one more. Check in order traversal of the given tree. Is not operate. It is zero because the value would be zero because in order traversal we are not actually doing anything. uh, we need to write it in point. There is no role of value parameter in this, so that is why we have not declared it to anyone. I must add that uh, in in this case I am not using modular programming, which is not really that good of an approach. But for better understanding of how actually everything works, I am writing it like I'm doing right now. So if you are actually writing for better performance and readability and less dependency on upon other code, then you must use modular programming. What I mean by that is that as we have written all of these methods in a single method, so we are using a single method for all of these functions, which is not actually efficient in real world scenario because this makes our code vulnerable to this method. So if something happens to this method, then whole code could crash. So it increases the dependency of all the functions to each other. Now, if I'm using modularity in my code and I'm declaring all these functions through distinct methods, then this code would be more secure and fast. Now, I don't know about fast, but it would be definitely efficient than this approach. And it would be very easy to add different functionalities and different checks to them. Last thing maybe I want to check in my main 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 function is that we have to search a value. Let's say we will search for 60 that is already present. BST dot update BST dot to be 16 dot search. Now let me run this command. Okay, we have already found 16, so our search works well. And if we see about the how our traversals are going, it is a very simple way to check what kind of traverse we are using. We know that the first node that we added was 50, which means that 50 is supposed to be a root in all the cases. So in order traversal states that the root would be in the middle of left and right. The root would be traversed after we traverse the left node. So we can see here as well that root node is actually in the middle of this data on these nodes. And in the pre-order, we define that the root value would be traversed first, then the left, and then the right. The same thing we can observe here, and if you apply the same logic, we can also confirm it with our output from post-order traverse. So this is how the code of binary search tree works. I hope you understood how to implement binary search tree. And if you have any questions, you can write it in the comments. Thank you for listening to my video.